How do we know that there was a Big Bang? And what the heck is it? Interestingly, the how question was solved in 4 different independent ways about the Big Bang. This is the best that science has to offer, actually. It's called independent confirmation. The first evidence for the Big Bang is actually a weird fact. The same way as when you ask why is the sky blue, you may ask why is the night sky black. And the answer to that has to do, believe it or not, with the Big Bang. Second support is the receding of galaxies. The third is the isotropic abundance of elements. The third is, that's the third. And the fourth is the microwave background radiation and its fluctuations. And that lecture will explain all of them. The last line here, the acceleration of the universe, is not one of those 4 pillars on which the Big Bang is standing. Rather, it's a recent discovery that we are still trying to fully understand. You may be asking yourself why we're out of order with book here. The reason is that the second proof of the Big Bang, the Hubble law, will be strongly correlated with dark matter and dark energy. Therefore, in today's lecture, you will see mostly the part about Hubble law, and that Hubble law is related to the expansion of the universe. So what is the Big Bang, really? I am letting you read here. So yeah, the Big Bang is the now well-established theory that what is now the observable universe was once smaller, compact, dense and hot. Nothing more, nothing less. By now you know that if we see as far as 100 trillion meters away, that's a distance that light would take about 13.7 billion years to reach us, which means that's 13.7 billion light years. Now that's the size of the observable universe. That's what we mean by the observable universe. It could be that there is something further still, but we can't detect it and we can't tell. So the Big Bang only relates to that part of a possibly larger universe that is now of the order of 10 to the 26 meters that was once much smaller and hotter. Here comes the next and much more sturdy pillar of the Big Bang. Edwin Hubble, the same guy that figured out that other galaxies were not in our own galaxy, that same guy that used Cepheids, those things that were discovered by Henrietta Leavitt, and found distances, he did the following. He started looking at further and further galaxies and looked also at their absorption spectrum. In the column under redshifts here, look at the middle stripe of light, the middle stripe of spectrum. Notice that you can see some absorption lines. Specifically, coming from the left, look for those 2 lines that are close together. Now look at the second triplet of spectra, in the middle one. The one for Ursa Major, which means that that's a galaxy in the Big Dipper. By the way, it's the same galaxy that in a previous lecture we've seen some variable Cepheid stars in there, so that's guaranteeing that the distance is correct. You can see that those 2 lines moved a tad to the right. Why? That represents an absorption line that's shifted towards the red. Notice how for Hydra, the one at the bottom, it moved all the way to the right. So the further away the galaxy, the faster it shifts to the red. Now if we remember the idea of the Doppler effect. Remember, if an ambulance passes you by and with a siren, the siren pitch drops as the waves stretch. If the ambulance moves really fast, the pitch drops further, which means that the redshift, the growing redshift, means that the galaxies are moving further away from us at a faster rate the further away they are. So as usual, I have a couple more questions for you, and I'll give you a few more seconds to try and answer them. Go ahead and read and see if you can get the right answer. Once you're done, check and see if you were right. When Hubble saw the graph that you're seeing in front of you, the further away galaxy, the faster it moves, he found it to be bizarre. Why should galaxies be moving away from us? If you look at particles in a gas, dust in the air, anything, things move away from us, towards us in all directions. Hubble, like Leavitt and Tycho Brahe, was an observer. He wasn't sure why that was. He just kept on measuring very carefully. The further he measured, the more the trend seemed to be correct. The last graph in this picture was done very recently, and it actually extends to 1/10 the distance to the edge of the observable universe. So why are those galaxies moving away from us faster the further away we are? Most people have an absolutely wrong view of the Big Bang that goes somewhat like the picture right below here. They think that there was a center from which everything exploded. Now, since everything is moving away from us, we have to be in the center of that explosion. Now, for one thing, that's exactly what we moved away from when we did the Copernicus revolution. Earth was in a center before that, then we put the sun in a center. Now suddenly we put our galaxy in the center. So that is leaving a bad taste, but there is another problem here. The Hubble law would not be right unless those galaxies that were furthest left first. So the further away galaxies should have different chemical composition of spectra. We don't see that. There are also some physics laws related with explosions that make this very unlikely. So this slide sucks because the Big Bang actually happened everywhere, in every point in the universe at the same time. Now, how can that be? The answer is that we have to use Einstein's general relativity theory. If you remember, that's what we did with explaining black holes. So we explained what happened near black holes, and we saw how the very massive object changes the direction of light. Here is what the universe can do in general, and what the following story does is it's a simplified story that explains this theory. It was developed by Einstein, then by 4 different people: Friedman, Lemaitre, Robertson, and Walker together. But the story is fairly simple. Assume there were 3 galaxies: Adam Galaxy, Eve Galaxy, and a Snake Galaxy. The universe grew to twice its size, but those galaxies remained the same exact size as they were. the distance between them grew from, say, 1 to 2. You can make it 1 megaparsec to 2 megaparsecs. And say that they grew, the universe doubled in 1 unit of time. Let's say 1 billion years. So let's see what Eve's reporting is happening. She says that Adam moved away from her at 1 per 1 billion years. There is 2 minus 1, which is 1 over 1. She looks at the snake and she sees the same thing. From 1 it went to 2, so it grew by 1 in 1. But Adam's telling a different story. He says that Eve is moving at 1 per 1 for him, but the snake is not. The distance to the snake grew from 2 to 4. So it grew in 2 in that 1 period. So the further away the object is, the snake is further, the faster it moved away from Adam. The universe expanded because energy from the high temperature changed into distances. And that is how Hubble law can work. So as usual, I have a couple more questions for you, and I'll give you a few more seconds to try and answer them. Go ahead and read and see if you can get the right answer. Once you're done, check and see if you were right. So as usual, I have a couple more questions for you, and I'll give you a few more seconds to try and answer them. Go ahead and read and see if you can get the right answer. Once you're done, check and see if you were right. A lot of lecturers use the same exact thing with balloons rather than Adam, Eve, and a snake. But you can see that the idea is about the same idea. Distance between two galaxies on a balloon grow from 2 to 4. From 1 to 2 or 2 to 4. Therefore, the further away you are, the faster you move. In 3 dimensions, you can do the same exact thing. That's why we placed those galaxy clusters in this picture in the same exact place, but made the cube in which they are double in size. Same thing. Double in size, the further away the galaxy, the faster it seems to recede from us. And that doesn't matter where we are in a cube. It's still going to be correct.